Hi there, this is Jude Socrates. Welcome to today's video on infinite series, where we are going to learn how to perform or obtain approximations using these power series representations that we have worked so hard to produce. So we will cover section 3E of our textbook. But before we go there, I wanted to show you a summary of many of the representations that we already worked on, plus a few that we haven't seen yet. So let's go to section 3K of our textbook. All right, here we go. So on one page, I have summarized some important power system. So starting, of course, with the basic geometric series, what started it all. And then when we did the calculus of representations, we took the derivative of both sides of this equation and then multiplied by x so that it was of a nice form. Instead of nx to the n minus 1, which looks unbalanced, we have nx to the n. So we obtained that representation. In the exercises, you did it one more time. So find the derivative of both sides of this equation multiplied by x, and then you get a series for summation n squared x to the n. Also, when we did calculus on power series, we took the antiderivative of the geometric series, and we came up with a series that can compute the natural logarithm for us. And we said that it converges for -1, but not for +1, because ln of 0 is still undefined. There's no getting around that. Then we had a big breakthrough when we talked about Taylor and Maclaurin series. So we started out with e to the x, and we saw that all of the derivatives are just e to the x. So it was easy to just to find the coefficients. E to the 0 is just 1. So these are simply summation x to the n over n factorial. Starting at 0, recall that 0 factorial is 1, not 0. In your projects, your assignments for last week, you did the hyperbolic sine and the hyperbolic cosine. And if you're not one of my students, we will see what these functions mean in just a minute. But also when we did Maclaurin series, we saw how to construct the Maclaurin series for sine of x and cosine of x, because derivative of sine is just cosine, derivative of cosine is minus sine, derivative of sine is minus cosine, and derivative of cosine back to sine. So remember that the four derivatives cycle. And of course, let's see, sine of 0 is 0. So only the odd terms survive for sine. And similarly, only the even terms survive for cosine. It's alternating because, what have we got? We saw cosine x and negative cosine x as some of our derivatives. Cosine of 0 is 1, negative cosine of 0 is -1. So that accounts for the alternating signs. Now, later in our textbook, we learn how to divide two series together. And you might say, wait a minute, how can you divide infinite number of terms? Now, of course, we truncate. We stop maybe at x to the 9 here, and we stop at x to the 8, and we perform a long division. It's kind of backwards though, because usually in long division, we have the highest power on the left and the lowest power on the right. We keep the order in this case, which kind of makes sense because the higher powers actually go to 0 as you approach the center of our power series. Earlier, again, when we did the calculus of power series, we did a substitution. We changed 1 minus x to 1 plus x squared, and then we integrated both sides of that representation because the derivative of arctan is 1 over 1 plus x squared. So by integrating 1 over 1 plus x squared, we get a power series for arctan. Arcsine is a little bit involved. It comes from what's called the binomial series. So instead of 1 over 1 minus x, we have 1 plus x to the power k. So here we have like 1 minus x to the power minus 1. The binomial series starts with the function 1 plus x to the power k, and then we take derivatives. In particular, we know that the derivative of inverse sine looks a lot like the derivative of inverse tan, if you remember. It's 1 over 1 over square root of 1 minus x squared. So yeah, there are some similarities between their derivatives. Arcsine, though, has a square root, power negative 1/2, because it's in the denominator. And instead of 1 plus x squared, you have 1 minus x squared. So they're kind of related to each other. And notice that for tangent, arctangent, and arcsine, only odd powers remain, just like we saw for the sine function. And that is because all of these functions are odd functions, and so only the odd powers of x are going to remain. All right, so I promised I would explain what the hyperbolic sine and cosine are. So yeah, they're sinh and cosh, and they're defined using the exponential function. Okay, sinh of x is e to the x minus e to the minus x over 2, and cosh of x is e to the x plus e to the minus x over 2. And you might say, what does this have to do with trigonometry? There's a surprise waiting for us. The derivative of sinh is cosh. Check out the power rule and the chain, I'm sorry, not the power rule, the chain rule. When you take the derivative of e to the x, you get e to the x. For e to the minus x, you get minus e to the minus x. So that minus becomes plus, and you get cosh. 1/2 is just a constant. Similarly, the derivative of cosh is just sinh. So e to the x stays e to the x, but e to the minus x becomes minus e to the minus x. So we get sinh. And of course, this should remind you of the regular trigonometric sine and cosine. Derivative of sine is cosine, but the derivative of cosine is negative sine. So that explains why in our representations up here, the representations for sinh look similar to sine, but sinh is not alternating. It's all plus. And for cosh, it looks like cosine, but again, it is not alternating. All right, so did I explain everything there? Anything else missing? So tangent using long division. There is a general formula for the coefficients of the tangent series, but it's kind of complicated, and it involves what are called Bernoulli numbers. Okay, so we explained how to do arctan in that video on calculus of representations, and this one we'll need a binomial series for arcsine. All right, so let's go now to the main event, approximations using power series representations. All right, here we go. So let's start off with some trigonometry. Here are the power series, the Maclaurin series for sine of x and cosine of x. And in our last video, we saw how to compute or approximate the sine function for a small angle, something like, 23 degrees. I forget what it was. Convert it to radians and then plug it into our Maclaurin series. Now, what happens if your angle is bigger? Okay, if you had 1,463 degrees, something like that. Well, of course, everybody knows that our sine and cosine are periodic functions. The period is 2 pi. So we can keep 2 between 0 and 2 pi, or 0 and 360 degrees if you like to think in degrees. However, we also have the sum and difference identities from basic trigonometry. And so if you add pi to an angle, the sine and the cosine simply change in sign, S-I-G-N, plus or minus, okay? And we know that's because if you have an angle and you add pi, you simply flip to the opposite quadrant. So what was positive will become negative, what was negative will become positive. All right, so that means that we only have to perform computations between 0 and pi, or 0 and 180 degrees. Excellent. Now it gets even better, because if you have sine of pi minus x using the same identity, you will just get sine of x, and if you get cosine of pi minus x, you will just get negative sine of x. So basically, we see some symmetry across the interval 0 to pi. In other words, we only have to compute sine and cosine in the first quadrant between 0 and pi over 2. Everybody should know that, right? If you know the value of the angles in the first quadrant, you can flip that angle or shift it to any point on the unit circle. So I'm probably telling you something that you didn't already know. Finally, if you may want to make it even smaller, we only have to rely on 0 to pi over 4, okay? That's because of the cofunction identities. Sine of pi over 2 minus x is the same as cosine of x. Cosine of pi over 2 minus x is the same as sine of x. So really, if you know the value of sine and cosine between 0 and 45 degrees, you know the value everywhere. Okay? So that's great, because pi over 4 is not a very big number. Pi is about 3, so it's about 0.76. Okay? So what does that mean? Well, we're going to take higher powers of x when we take the Maclaurin series of sine and cosine. 0.76 to the power 7 is very, very, very small. Okay, so these terms are going to get smaller and smaller, close to 0, if your x is between 0 and pi over 4. Okay, let's go to the workroom and demonstrate that. Okay, so we want to approximate the cosine of 217 degrees. Okay, so 180 is to the left, and then 217 is not far from 180. So if we subtract 180, 217 minus 180 degrees, we are going to get 37. Oops, not to the power 8 degrees, 0. So I'm just improvising. 37 degrees. Okay, so that is between 0 and 45 degrees, so we can directly plug it into our series for cosine of x. But first we have to convert it to radians. So our x will be 37. Again, we saw this in the last video. We need the conversion formula, pi over 180 degrees, that's 1 essentially. So the degrees unit cancel between 37 and divide by 180, and then we multiply by pi. So that is approximately 0.645. Okay, so it's even smaller than 0.75, what we were talking about earlier. Of course, that's smaller than 45 degrees, a lot smaller, quite a bit smaller. Okay, so we're going to plug this into the cosine series, and it's alternating. We're plugging in a positive number. So the error formula for the maximum error for an alternating series says that the maximum error is the term that you are not adding, the next term that you're not adding. So do you feel lucky? Let's see. Let's try x to the 4th power. Maybe you're going to be enough. So our x is this number. We want its 4th power and divide by 24. I think that's still going to be, oh yeah, it's not that small. Okay, 0.7 times 10 to the minus 3. So let's try 6th power. Okay, so x to the 6 over 720. Replace, and what you got? It is, okay, that's better. It's about 10 to the negative 4. Okay, but again, I've told you that if you already computed the number, then you might as well add it in. So the error is actually, if we include this, it's going to be this amount. So yeah, it will be smaller than 10 to the minus 5. Okay, so let's plug in the others. We have 1 minus x squared over 2 missing. So let's plug this one in. Square divided by 2. You all know how to work your calculator. We have the 4th power here, and then we subtract the 6th power over 720. Okay, so that is approximately 0.79863. Okay. So, I forgot something. When we subtract 180, yeah, we do get a nice angle, but the cosine changes sign, S-I-G-N, because it's in the opposite quadrant. So therefore, thus, cosine 217 degrees is approximately the negative of 0.7983, blah, 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 blah. Okay, it's negative. Okay, if you want to compare this to what your calculator would say, yeah, you go ahead and plug that in. We want 217 pi over 180. Okay, because Maple will not recognize that symbol. I'm just making it up. 180. And we get approximately, yeah, there you go. 8635. Okay, so the 4 here is different. So yeah, but we get 47 here and 55. So that difference is about 8, right? So, and the 8 will be 1,000,000,008, right? So that's a pretty good approximation. Okay, so let's go back to our PDF and let's take a look at logarithms. All right, so here is our Maclaurin series for the logarithm, although actually we did use the geometric series to find this by integration. We know though that if there is a power series for a function, it must be its Maclaurin series when you center it at 0. Okay, so unlike sine and cosine, this is not an alternating series if x is positive. But if x is negative, in other words, between -1 and 0, then you do get minus, plus, and so on when you take these powers. So we can use the formula for the maximum error of the alternating series if we're plugging in x is a negative number. In other words, if x is negative, then you'll get 1 plus something between 0 and 1. So it will be the ln of a number between 1 and 2. All right, so let's execute this process. So what if we wanted ln of 0.35? Okay, not a very big number, 0.35. So the tricky part is solving for x. Not really that tricky. Okay, so 1 minus x, we want to be 0.35. So x is basically just 0.65. So minus ln of 1 minus 0.65 gives us negative ln of 0.35. Okay, arithmetic. We plug in 0.65 into the first few terms. Okay, so everything is positive. We don't have an error formula. Let's just do that. So square over 2, cube over 3, and so on. Add it together. You'll get about 1.02, but move the minus to the other side. Okay, so that makes sense. The ln of a number between 0 and 1 should be negative. You remember how the ln looks like its graph. Okay, so that is a reasonable answer for ln of 0.35. Okay, and of course, if you check in your scientific calculator, you'll get a similar answer. Where is it? We got minus 1.02, and now we get minus 1.05. So it's not that great, okay? Again, because we don't have an alternating series, the error is not good, even with 5 terms, power 5. Okay, so try again. What if you want ln of 1.42? Okay, so this time it's between 1 and 2. Solving for x, you want 1 minus x to be 1.42. So x is negative 0.42. Okay, so this time it's an alternating series. If we kept the powers up to the 5th power, the error will be the 6th power over n over 6. So yeah, it's not that great either, but it's much better. 001 practically is the error. Okay, so now plug that negative 0.42 into your power series. Again, mindful that the minus sign will move to the other side. You'll get the negative approximation to the right first, but the minus signs will cancel to give you a 0.3513, and that is not too shabby. It's comparable to what your scientific calculator would give you, about 0.3506. So yeah, we do have a difference of about 0.0007, something like that. Okay, so what happens if your number is not between 0 and 2? Okay, after all, you could want to find ln of 40 or ln of 112 and so on. Okay, well, one way to do it is to shrink that 40 so that we get a number which is between 0.5 and 1.5. So why are we picking 0.5 and 1.5? Remember that 1 minus x will be between 0 and 2. Okay, so 1 is the axis of symmetry of that interval. So when our 1 minus x is between 0.5 and 1.5, the error should be much better than if it were, let's say, 1.8 or 0.2. Okay, so the terms should approach 0 very quickly. Now, what's the effect of dividing a number by e? Okay, so if you keep dividing by e, eventually you'll get a number which is between 0.5 and 1.5. Okay, how many times? 1, 2, 3, 4. So e to the power 4. 40 divided by e to the power 4 gives us 0.73 something. So solving for 40, you'll get e to the 4 times 0.7 something. Now we have the product rule for ln's. Okay, we know that ln of a product is the sum of the ln's. So ln of 40 should be ln of e to the 4 plus ln of this thing. But ln of e to the 4, you have the cancellation property. That's just 4. Okay, so we have 4 plus ln of 0.732. Now we're back to what we know how to do. Just plug it in directly into the series. So let's demonstrate this in our workroom. Let's pick a number bigger than 40. Okay, how about something like 73? Okay, let's do something like that. All right, so here's our power series for the logarithm. We want ln of 73. Okay, so how many times will we have to divide 73 by e to get a number between 0.5 and 1.5? There's 1. And so we take this and divide again by e over e. And we get, okay, getting close. So now we take this and you divide by e. One more time. And not yet. One more time. So we get divided by e, and we get 1.33. Okay, we are within 0.5 and 1.5. So how many times is that? 1, 2, 3, 4 times as well, just like we did for in the text. Let's just compare. What happens if we do it one more time? Are we going to go below 0.5? let's see, just under 0.5. Okay, so let's keep it at 1.337. Okay, so this says that 73 divided by e to the power 1, 2, 3, 4 gives us 1.337. Okay, so let's do this. Divided by e to the fourth power gives us 1.337. And, just to be sure, did we count correctly? We get, 1.337. Okay, so let's put our power series at the bottom because we're going to need it there. Let's just make a copy. Okay, so we want 1 minus x to be this number, 1.337. Okay, so x is going to be negative, yes, negative 0.337 and so on. Yeah. Okay, so that's good because we're going to get an alternating series. So what happens if we take the 6th power over 6 and we get approximately 10 to the minus 4. Okay, I'll accept that. That's fine. Okay. So we're going to take up to x to the 6 over 6, since we already computed it. So we deserve to add it on. But I'm going to cheat and just ask Maple to plug in x into each and every term of this expansion. And Maple says we get negative 0.29. Okay, so this gives us, so minus ln of 1 minus x, which is this 1.337, equals minus 0.29, blah, blah, blah. And so we can cancel both sides, the minus sign. ln of 1.337 is positive 0.29. Okay, so how does this relate to our ln of 73? Okay, so we have this equation. Back to our main program, we said that 73 over e to the 4 is this much. So 73 equals e to the 4th power times 1.3704 blah, blah, blah. And by the product rule, ln of 73 is the ln of this product, which we know is the ln of e to the 4 plus outside plus the ln of this factor. And of course, ln of e to the 4 is just 4. So we will get 4. That is just 4. 4. I'm sorry. Where am I? Math. So we have equal to 4. Yeah. Plus ln of this. Okay. And we saw that the ln of this thing is this much. So we are going to get, whoops, I did not copy. We want 4 plus this much, or simply 4.29, and so on. Okay, so we get our final answer, 4.29, and so on. All right, so yeah. Oh, great Maple, did we do it right? What do we get? ln of 73 is about 4.29 and so on. Ooh, my bad. My screen is bleeding over to the left side. Oh well, it's just my directory. All right, so let's go back to our PDF and I can fix the screen. All right, power series are incredibly good at helping us compute or approximate definite integrals, especially for functions where we have no idea what the antiderivative is. Okay, so we've seen examples like this in our video about Simpson's rule, trapezoid rule, remember those? And we also learned how to find error approximation for those. They were a pain, remember? You had to subdivide into 8 subintervals. You got to plug in your function, the endpoints, and then there was this pattern, 1, 4, 2, 4, 2, 4, 1. Yeah, that was not fun, was it? But you also got to play with the triangle inequality and say, okay, I can say with confidence that the error is at most this much, and so on. Okay, but yeah, even GeoGebra will not find you the antiderivative, but it will tell you that the integral is approximately 0.9774. Okay, so of course, the idea of doing this is a power series along with the substitution. Okay, so let's do something similar. Let's integrate this for sine of maybe x cubed. Let's try that. Okay, but instead of square root of pi over 2, let's have our upper limit as cube root of pi over 2. So that at this point, we'll get sine of pi over 2, which is 1. The graph will look a little bit nicer. Does it have to be that? No, of course not. We can have it as just 1 or even 3. Integral from 0 to 3. Why not? Okay, so we have our Maclaurin series for sine of x here, but we want sine of x cubed. So we will perform a substitution. Let's copy the main series here, including up to that minus dot, dot, dot. Maybe not the dot, dot, dot. So we want x cubed. Okay, so replace x with x cubed. And you'd better use parentheses, especially for these terms over here, because we are gonna get x cubed cubed, x cubed to the 5th, x cubed to the 7th, and x cubed to the 9th. And everybody knows their rules for exponents, don't we? Don't we? So we have x cubed to the 3rd is x to the 9. X cubed to the 5th is x to the power 15. There you go. X cubed to the 7 is x to the 21. And x cubed to the 9th is x to the 27. There you go. So 3, 9, 15, 21, 27. 3 to 9 is 6, 9 plus 6, 15, 15 plus 6, 21, 21 and 6, 27. Okay. So, when you plug in 0, hang on. Ooh, I almost made a big boo-boo. So this is sine of x cubed, but we're integrating, okay? So we need the antiderivative of this expression. And I'm going to use brackets because, as I've mentioned in the past, this would look very nice with round parentheses. Okay, so it's basically just the power rule, of course, when you're taking antiderivatives. So we have, I'm going to borrow this. X to the 3rd power becomes x to the 4th power over 4. Okay? And then what about the rest? So let's change this. So x to the 9 becomes 10 over 6 times 10, 60. 15 becomes 16 over 16. So 120 times 60. We'll let Maple do the hard work for us. 21 becomes 22 over 50/40 times 22. And 27 becomes 28 over that number by 28. Okay, excellent. So these are the first 5 non-zero terms for the antiderivative of sine of x cubed. Okay? If you plug in 0, of course, you'll get 0. Oh, remember when we did this in the first video on the calculus of representation? There was a plus c, right? But we don't need that here because we have a definite integral. So no need to find that c. Okay, this is the x, though, that we're going to plug in here. And still an alternating series. So fortunately, we can use the maximum error formula for the alternating series. And I'm willing to bet that this number is already very, very small. So if we try that in this term, and we are going to, and careful, wrap it in parentheses when in doubt. And remember your order of operations when you're doing this by hand. So, ooh, okay, still a good size, 0.056. So let's go to 22. Okay, let's make it more accurate. I can afford to do that. We have a computer doing the hard work for us. So this is our x, and to the power 22 over that denominator. Okay, that's good. Okay, we will accept that. So why did that happen? Pi is 3 point something. Pi over 2 is bigger than 1. So even if you take the cube root, you'll get the number which is bigger than 1. So it's not like we're getting close to 0 very, very quickly. Okay, so again, we'll have GeoGebra, no, not GeoGebra, this is Maple doing the hard work for us. And we will ask it, would you kindly plug in our x into that whole mess? And you know how to do this by hand on your calculator, of course. So we are going to get 0.38969 and so on. Would you like to see what would happen if we add one more term? Is it going to be much different? So let's add the 28 power right there. Okay, do we get much of a difference? So we get 8694. I see. So 44 is now 51. So the difference is about 1, 2, 3, 4, 5 zeros and maybe a 6 or a 7. Okay. So, 44 to 51. Yeah, that's about 7. Okay. So, fortunately, we can ask GeoGebra to approximate this integral for us, as we saw in our textbook. All right, so I already graphed our function between 0 and cube root of pi over 3, pi over 2, and we want the integral of f of x between 0 and pi over 2 to the power 1/3. Power and 1/3. And we get, looks familiar, 0.3869511. And I believe this is pretty close to the approximation that we got when we added that one more term. Okay, so of course, we can make this as accurate as we want because we had an alternating series and you know the formula for the maximum error. It's just tedious if you add a lot of terms. But is it more tedious than Simpson's? Divide into 8 subintervals, plug them into your function. Yeah, of course, in this example, we had to plug in our x into a power series. Okay, so we had to plug in the same number into x to the 6, x to the whatever, and then I add them all together. So yeah, it's not like it's a lot easier. It's just a different kind of computation. You don't get anything for free. All right, so that is our video for today. So until next time, I hope you enjoy the rest of your day. Bye.